Okay, in the last class, we had started discussing the idea that LTI systems, whether continuous or discrete time, are completely described through the use of one. If we know the output of one input, which is the impulse, we know output of every input in LTI systems. And in the continuous time, we looked at, in both cases, it's described through the convolution formula. In continuous time, we looked at the convolution formula. In discrete time, the convolution formula is, of course, takes the summation form. So for discrete time LTI systems, the output is convolution of input and the impulse response, which is simply equal to just an analog of the continuous time operation, except instead of integration, we have now summation. So h of m, or equivalently, m minus infinity to infinity, x of m, h of n minus m. And the principle of flip and slide still apply. So this is exactly, you can think of it as a, if you want to understand that, it's the flip and slide rule where you are fixing one function, xm or xn, doesn't matter what I use for the variable. And then you are flipping the other function, so because this minus m is the flipping operation, and then you are sliding it either to the right or the left, depending upon what value of n is. So if you want to evaluate y3, you slide it for n equal to 3, you multiply by the two functions, and then instead of in the continuous time where you do the integration, in discrete time you do the summation. So here is a pictorial representation of the convolution where this is h, this is the impulse response, this is the x is the input. We are going to fix the input, so x of k is fixed. We first flip the impulse response, so this is the flipped version. And then for each output, if we want to compute the output at, let's say, n equal to 0, we basically slide it by 0, which means we don't slide it. We multiply the 2. So this is the multiplication of this thing and this flipped version. And then once we multiply, so the multiplication is going to happen pointwise, right? 2 multiplied by 1, we get 2 here. 1 multiplied by 2, we get 2 here. This is 0 multiplied by a thing, so everything here is 0. And once we do the pointwise multiplication, we just add all the things up. So 2 plus 2 is 4. So we get this, which means y of 0 equals 4. Now, if you want to compute y of 1, then you look at this flipped version and you slide it by 1. Right? So this 2 basically comes here and everything gets shifted to the right. You do the multiplication again. So this is what the multiplication looks like. 2 times 1 is 2, 2 times 2 is 4, 1 times 3 is 3, and then everything else is 0. And then you add them all up. The sum you get is 2 plus 4 plus 3, 9, and that is y1. Okay. And the similar thing you can do for other cases. This is what you do. For n equal to 2, you slide it by 2. You slide the flipped version by an amount of 2. Again, you multiply, you add them up, and you get 11, which is y of 2. And if you can do the same for negative values of n, which means you would slide the thing to the left. Right? So this is n equal to 1, and you are sliding the flipped version to the right. For n equal to minus 1, you will have to slide it to the left. For n equal to minus 1, you'll slide it to the left, and then you will still do the same thing. Multiply whatever you get to your x, add them all up, and that will be your y of minus 1. Okay. So in time domain, understanding what LTI systems do is really easy. It's convolution. But getting an intuitive handle on what these LTI systems are doing by looking at this convolution expression is really hard. Right? If I give you the a convolution expression, if I give you two LTI systems and I show you their convolution summation, it will be a hard task for us to be able to determine what one LTI system is doing compared to the other. Okay? Interpreting the time domain operation tends to be not that intuitive. So to really understand the crux of what LTI system is doing to the input, that's what we want to understand. We want to figure out what is the LTI system doing to the input so that we can design the right systems. Okay. Now, understanding that in time domain is really hard. So what we do is we look at signals and LTI systems in some transform domain. So by this time, you guys have looked at many different types of transforms. Just a reminder, what is a transform? A transform is just another way of looking at the same signal. The analogy that you may want to take is, for example, a quarter, a coin, quarter coin, which has heads and tails. Now, whether I show you the head or the tail of that coin, you know what that coin is. It's a quarter, right? So we can either keep on showing you the head version of that or the tail version of that. It is the same coin. That's the view that you should take of transform. A transform is nothing but looking at the same thing, the same signal in a different manner than just looking at the time domain version of it, right? In time domain, the signal is varying, or the LTI system, the impulse response is varying in a certain fashion. Transform domain says, let's look at it in a different way and see if we get some more information. Now, transforms are really bread and butter of signal processing, and there are different types of transforms. So uses of transforms can range from uses of transforms. There can be two big reasons for using transforms. One big reason is simplification of analysis. So sometimes we want to do some analysis which ends up being really messy if we do it in the time domain. An example of that is solving differential equations. Okay. So solution of differential equations, if you try to solve it by itself, can be really hard. What is a good transform to use for solution of differential equations? Laplace transform. Right? So Laplace transform, an example of that will be helps us with solution of differential equations. That's just one use of the Laplace transform. But in general, transforms can help us do simplification of analysis. And there is another reason we want to use transform, which is that they provide insights into the nature of signals and systems. Okay. So while Laplace transform can be explained in terms of physical aspects, there are some other transforms which are directly related to the physical properties of signals and systems, and that's why we use them. So what's the immediate counterpart when you tend to think of time and you say you have a signal which is a function of time, which means the signal is varying? There is a counterpart to that time parameter, which if we understand that counterpart, that concept, we can say something about the signal. And that is, if something is wiggling, associated with it is this notion of frequency. Right? So in the case of LTI systems, what we want to do is LTI systems and signals are given in terms of time. Right? We have signals which are functions of time. We have outputs which are functions of times. And we have LTI systems which are described as this impulse response, which is again a function of time. Now, when we are thinking of in terms of time, something is wiggling, we can associate with that the notion of frequency. So oftentimes what you hear is that time and frequency are dual of each other. Right? Intuitively, all of us, whether we understand mathematically that concept completely or not, all of us understand what is the meaning of frequency up to a certain level. So heuristically, frequency can be defined as the rate at which something changes. And by something will often be, it has to be function of some variable. We'll assume that variable to be time. Okay. So if something has high frequency, we say it changes very fast. If something has low frequency, it changes very slowly. Okay. Now, we can associate the concepts of frequency to every signal, but mathematically, the notion of frequency applies at how something is changing in a periodic fashion at what rate. Right? So there are signals that change at fixed rates or frequencies, as we will call them. And those are sort of the fundamental building blocks of, if we want to talk about frequencies of any arbitrary signal. Okay? So what are those signals? They are periodic signals, and we often associate the term frequency with sinusoids. So those are the fundamental building blocks. We can have, for example, a sine 2 pi 200t. Right? This is a periodic signal. It is changing at a fixed rate. What is the rate that it is changing at? The rate at which it is changing at is 200 hertz, which means it completes its cycle 200 times every second. Right? Cycles per second, that's what hertz is. And you can, of course, convert it to radians, which is just 2 pi times 200 radians per second. Cosine is another example. It's for example, if I have 2 pi 4000 t, right, this thing is changing at 4000 hertz, which means that this cosine signal is going to have 4000 cycles per second. Right? If you plot this cosine, it will change 4000 times in 1 second. It will have 4000 cycles. And of course, complex sinusoids, which are nothing but cosine plus imaginary times sine. So if we have e to the j 2 pi 8000 t, again, this is a complex exponential complex sinusoid which has a frequency of 8 kilohertz, which means that if you think of it, it completes 8,000 cycles per second. So these are fundamental building blocks, or if you want to talk about frequency, then what our goal is that we want to understand. So these are periodic signals. We understand the notion of frequency, but using these fundamental signals, these fundamental concepts of frequencies, what we want to do is be able to interpret any arbitrary signal in terms of frequencies. Okay. In general, if I just show you an arbitrary signal which is not periodic, you can't associate a single frequency with that signal. Okay. So the right transform, if you want to now understand signals and impulse responses of LTI systems in terms of frequencies, the right transform for that is transform for studying frequencies is called the Fourier transform, named after the guy who first understood that any signal, any arbitrary signal can be thought of as made up of many frequencies. Okay. So transform for studies frequency is called Fourier transform, depending upon whether we are studying continuous signals or discrete signals. It's called continuous time Fourier transform, discrete time Fourier transform. So in this case, right now, I'll just remind you of the continuous time Fourier transform because you have studied it in the previous class. I'll use CTFT for short. Okay. So Joseph Fourier, a famous mathematician, was the guy who basically understood this concept, and the Fourier transform is named after him. What he said was that every signal x of t, okay, that is finite energy, and we'll look at what does finite energy mean mathematically. It doesn't matter the signal is periodic or not. The signal could be wiggling in an arbitrary fashion. That signal, if it is finite energy, can be thought of as consisting of complex sinusoids of different frequencies even if the signal is even if x of t is not periodic. Okay. So I just want to repeat what I said earlier. Frequency, the concept that is applied as mathematically was stated earlier, is hertz, cycles per second. If you want to talk about cycles per second, you have to talk about periodic signals. Now, arbitrary signals, for example, my speech, is not periodic. But what Joseph Fourier said was that if you give me any arbitrary signal, even though I can't associate one frequency with that signal, I can show that that signal is made up of many, many frequencies. Okay? And the mathematical way of doing that, we call that continuous time Fourier transform. So continuous time Fourier transform is really the key to understanding the frequency content of signals or impulse response of systems. Let me just define the meaning of finite energy. Finite energy in terms of continuous time signals means that If I take the absolute value of my signal, I square it, and then I take the integral, then that in total is less than infinity. Okay. So if a signal satisfies this condition, it's bound to have been made up of many frequencies. Okay. So you all have done many Fourier transform pairs and you understand those, but the key thing is, while you may be very good at solving the mathematical side of continuous time Fourier transform, what you need to really understand is that continuous time Fourier transform is effectively telling you the frequencies which make up your signal. And the frequencies means it gives you both magnitude information about that frequency and phase information about that frequency. Okay. So just to explain this concept a little better, for example, let's say that you have x of t, which is given by 4e to the j pi by 4 e to the j 2 pi 8000 t. Right? And you can write it as a times e to the j 2 pi 8000 t, where this a is 4e to the j pi by 4. If I give you this signal, you can explain what this signal is. This is a signal which has one frequency of 8000 hertz or 8 kilohertz. The amplitude of this frequency is 4, and the phase of this frequency is pi by 4. Right? Now, so while interpreting that is easy, I could now also give you, for example, two of these signals. I could say that my signal is made up of a e to the j 2 pi 8000 t plus another complex number b e to the j 2 pi 4000 t. Right? And now if you look at this xt, you can say, oh, this signal is now, I can't say this is made up of one frequency, it is made up of actually two frequencies. It has one frequency of 8 kilohertz, the other frequency of 4 kilohertz, and you can look at what is the amplitude of 8 kilohertz frequency and the phase of 8 kilohertz frequency. You can look at what is the amplitude and phase of 4 kilohertz frequency. So continuous time Fourier transform essentially extends this to an infinite number of frequencies. Okay, we started with one frequency, wrote it as sum of two. If we have infinite number of frequencies, well, if you think of the Riemannian sum, we can write it as an integral. So that is effectively, if you think of the inverse continuous time Fourier transform formula. Okay, we'll go to the continuous time Fourier transform formula by starting with the inverse first. So what that says is that x of t is equal to 1 over 2 pi. You have an integral minus infinity to infinity. You have something x of j omega, which we call the continuous time Fourier transform, and e to the j omega t d omega. Okay. So let's try to interpret this inverse continuous time Fourier transform and the x of t that I wrote as sum of two frequencies. So first of all, what is this integral? Well, this integral, you should really think of it as an infinite summation of very small frequency units, right? Think of the Riemannian sum, how that goes to the Riemannian integral. Now, if you think of this integral as the summation, then let's look at this. What is this thing saying? And compare to this case. This is saying that you have a sinusoid with frequency capital omega. And that frequency is being multiplied with something x of j omega, okay, which is a complex number. So what the inverse, if you look at the inverse continuous time Fourier transform, what this is saying is that x of t is made up of an infinite number of sinusoids and the frequencies of those sinusoids range from, so this integral has limits for the frequencies, right? So it goes from minus infinity to infinity, which means it consists of infinite number of sinusoids of frequencies ranging from minus infinity to infinity radians per second. So this inverse continuous time Fourier transform is in radians per second. So what this is saying is it is made up of infinite frequencies, and what is the amplitude and phase of each frequency? The amplitude and phase of each frequency is given by this quantity x of j omega. So if omega was, let's say, 2 pi 2000, like 2 kilohertz, then, and you want to find out what is the amplitude and phase of that 2 kilohertz frequency, you look at x of j omega at that value. Okay. So x of j omega, it tells us about the amplitude and phase of the frequency omega present in x of t. Okay. So if someone asks you, does this signal have 2 kilohertz frequency present in it? What you do is 2 kilohertz part of xt? Well, for that, what you need to look at is x of j 2 pi 2000. You evaluate that. And if this is equal to 0, then you know that that signal does not have the 2 kilohertz frequency. If this is not equal to 0, then you say, so this versus you could have x of j 2 pi 2000 could be equal to, let's say, 2 e to the j pi by 3. In that case, you will say, yes, x of t has the 2 kilohertz frequency present, and the amplitude of that frequency is 2, and the phase of that frequency is pi by 3. Right? So this x of j omega, that is what is called the Fourier transform. So technically, we call x of j omega as continuous time Fourier transform of x of t. And the way we define that is x of j omega equals minus infinity to infinity x of t e to the j capital omega t d omega. Okay. So the point of all this discussion is that continuous time Fourier transform is a surrogate for telling us which frequencies are present in the signal, what is the amplitude of those frequencies, and what is the phase of those frequencies. And the inverse continuous time Fourier transform basically confirms that x of t can be just written as a superposition of an infinite number of frequencies whose amplitude and phase is given through the continuous time Fourier transform. So let's just take a simple example to clarify this point of what is the purpose of continuous time Fourier transform, which is just telling us which frequencies are present, what is their amplitude, what is their phase. So let's take the example of a signal which is actually just a pure frequency signal. So let's take x of t equal to 2 pi 2 cosine of 2 pi 1000 t, which means it's a 1 kilohertz sinusoid and its amplitude is 2. Now if I look at its Fourier transform, x of j omega, the Fourier transform ends up being 2 pi delta of omega minus 2 pi 1000 plus 2 pi delta of omega plus 2 pi 1000. So we are just trying to confirm that this is really the case that Fourier transform tells us about the frequency. So we start with a signal that we know what the frequencies are. This signal is a pure sinusoid and it has two components. It has, if you think of in terms of the complex sinusoid, it has minus 1 kilohertz and 1 kilohertz frequency present in it. Right? So this is the continuous time Fourier transform. And if we plot it, it has basically an impulse at of area 2 pi at 2 pi 1000 in radians per second. If I were doing hertz, then I will get rid of the 2 pi in the x-axis. And at minus 2 pi 1000. This is my x of j omega. So indeed, if I were to show you this x of j omega, you will know that this signal has only minus 1 kilohertz and 1 kilohertz frequency present in it. Okay. Now, the other thing which you should always know is that pure sinusoids, and by pure I mean either cosine, sine, or complex sinusoids, always appear as impulses in continuous time Fourier transform. Okay? Pure sinusoids always appear as impulses. So if you get a continuous time Fourier transform plot which has some impulses, those impulses correspond to the fact that the input signal had some pure sinusoids in it. Okay? If it has no impulses, then it did not have any pure sinusoid. It's made up of many other frequencies. So that's the definition of what, or that's the meaning of what does continuous time Fourier transform do in terms of helping us understand the frequency content of input signal. If you had a way, what you would do is, for example, be able to plot my voice as a function of time, x of t. You can compute the continuous time Fourier transform of that x of t, and then you will know exactly which frequencies are emitted when I am talking. Okay. Or if you are playing some piano and you are worried that a note on the piano does not have the right frequency, if you had a way of writing that output of that piano, that signal, as in terms of mathematical expression and compute its continuous time Fourier transform, you can look at the values of that continuous time Fourier transform, will be able to say, okay, this piano is really playing the right tone or not by looking at the locations of where the impulses are in your Fourier transform. Okay. So this helps us understand what does the Fourier transform tell us about signals. Now what we need to understand next is how to interpret operations of an LTI system. In terms of frequencies. We understand signals. Now we are trying to understand what do systems do in terms of frequencies. So for that, what we need to remind ourselves is that every LTI system, first of all, is fully described by an impulse response. H of t. Okay. So assuming that this impulse response is finite energy, because the condition for computing the continuous time Fourier transform is finite energy. So assuming h of t absolute value square dt is less than infinity, mathematically we can compute its Fourier transform. We can compute the Fourier transform of h of t, and we can see which frequencies are present in h of t. We can compute the frequencies present in h of t. Okay. And we'll write that as h of j omega, continuous time Fourier transform. Okay. So since every LTI system is associated with an impulse response, that impulse response has some frequencies present in it. So we can say every LTI system is associated with some frequencies. But what is the meaning of those frequencies? Because the meaning of frequencies in input signal is which frequencies are present in it. But LTI system is not a signal. So what does it mean that the impulse response has these frequencies present in it? For that, we need to look at the convolution property of the Fourier transform, which I'm sure all of you have looked at in your previous course. So we'll just remind ourselves that if I have a signal which is given by convolution of two signals, then the Fourier transform of that output, y of j omega, is equal to multiplication of their respective Fourier transforms. Okay. So let's remind ourselves where does convolution appear in LTI systems. So our output of LTI system is given by convolution of xt and y of t. The convolution formula says that the Fourier transform of y of t is nothing but multiplication of the Fourier transform of input and the Fourier transform of LTI system's impulse response. So what does it mean physically though? Let's ask ourselves, what is x of j omega? X of j omega is telling us about frequencies in x of t. What is y of j omega? Y of j omega is telling us about frequencies in y of t, the output. So what does this expression then mean? What does this expression mean? This expression says that my output frequency, the frequency omega in my output, is nothing but the multiplication of the amount of frequency present in my input times the frequencies present in my impulse response. Okay? So this is an expression which is saying that the LTI system, in terms of frequencies, the LTI system, the action it is doing is it is multiplying the magnitude and it is changing the phase of my input signal by the magnitude and phases of my impulse response. So what we want to remember is that LTI systems do this expression, x of j omega, h of j omega, and there can only be three things that it can do then. Okay. The first case is if x of j omega equal to 0 for some omega. What I mean by that is, let's say that example is, let's say x of j 2 pi 1000 is equal to 0. Okay. So whenever I put omega, it means that I'm talking about any arbitrary frequency. Okay. So if x of j omega equal to 0 for some omega, the example being, let's say for 1 kilohertz it's 0, what does that mean? That means that the input signal at that has no frequency of 1 kilohertz. So this means if I'm multiplying my y of j omega equal to x of j omega times h of j omega, my y of j omega has to be equal to 0 also. So for example, if I take that example, y of j 2 pi 1000 will have to be equal to 0 regardless of what h of j omega is, regardless of what the LTI system's impulse response Fourier transform is. So what does it mean? That an LTI system, if my input signal has no frequency present at some value, okay, if my LTI system, if my input signal has no frequency at, let's say, 1 kilohertz, the output of the LTI system cannot have that frequency either. So LTI system cannot generate new frequencies. Okay, that's the first key concept. If my sound does not produce, let's say, 2 kilohertz frequencies, if you use an LTI system to process it, you cannot add 2 kilohertz frequencies no matter what you do. The other case is that LTI systems can either scale up or scale down frequency originally present in the input signal. So again, take the example of omega equal to 1 kilohertz or 2 pi times 1000 radians per second. So if, for example, my x of j 2 pi 1000 is, let's say, 3 e to the j 5 pi by 6, which means that my input signal has a 1 kilohertz frequency, which has amplitude 3, phase 5 pi by 6. And let's say that h of j 2 pi, okay, is 1.5 e to the j 7 pi by 8. So if you want to understand what will be the output frequency, what will happen to the frequency at the output of 1 kilohertz, you need to look at the input frequency of 1 kilohertz and the impulse response Fourier transform at 1 kilohertz. So my y of j omega at 1 kilohertz will be simply multiplication of the two, which is 3 times 1.5, which is 4.5, e to the j 5 pi by 6 plus 7 pi by 8. Right? So this is a case where my output frequency at 1 kilohertz is now has a higher amplitude than my input frequency. So that's the concept of scaling up of frequencies. Let's say you really like bass in your songs, you can go to 18 kilohertz frequency and you amplify it, you scale it up. Okay. On the other hand, if h of j2 pi had a magnitude of, let's say, instead of 1.5, it had a magnitude of 0.5, your output frequency of 1 kilohertz will have magnitude of 1.5. So that will be the case of scaling down of frequencies. Okay. So that is one of the other things that LTI systems can do. If your input signal already has some frequency, it can either amplify that or it can damp it depending upon what is the Fourier transform of your impulse response at that frequency. Okay, the key part is at that frequency. Now the third thing, as you can see even from here, is that LTI systems change the phase of input frequencies. Can change the phase of input frequencies. And the example we'll just take from here, right? This was an input frequency with a phase of 5 pi by 6. Because your h of j 2 pi 1000 had a phase of 7 pi by 8, your new phase is 5 pi by 6 plus 7 pi by 8, and then you will wrap it by a factor of 2 pi. So it changed the phase of your output frequency. Okay? And so it didn't change the it may not change the contribution of the frequency in your output, but it can change the phase of your output frequency. Okay? And that can have an impact if all the frequencies are not changed by the same phase. And the last thing is that if x of j omega is not equal to 0 for some omega, but h of j omega equal to 0, then what will happen? You multiply two numbers, one of them is 0, the output has to be 0. So y of j omega will be 0 regardless, regardless of whether your input frequency was 0 or not. What does this mean? That LTI systems, while they cannot add new frequencies, they can kill existing frequencies in the system. So LTI systems can kill some frequencies. In the input signal. Again, if you take this example where you have x is non-zero at 1 kilohertz, but if you designed an LTI system whose h had a Fourier transform which was 0 at that value, then your output signal will have no frequency at 1 kilohertz. Okay? So LTI system will effectively kill that frequency off. And that's an operation that is used all the time in LTI systems. Okay. The analogy, if you really want to think of LTI systems, right, is really the analogy of equalizer, which is an equalizer is nothing but an LTI system which is just changing, either scaling up or scaling down the frequencies. So this is a traditional equalizer that you will see, right, where these things list the frequencies. Right? This is 20 hertz and it goes up to 20 kilohertz. So this is an equalizer which is, you are telling this equalizer by scaling these things up and down, effectively you are designing, you are changing the frequency response of this LTI system. If you have your knob at the center, you are saying leave that frequency unchanged. If you take it above 0, so these gains are typically in decibel, okay? If you take them above 0 decibel, which is more than 1 in absolute value, you are saying, so this equalizer is scaling up these frequencies. This is saying, I want you to increase the magnitude of these frequencies. Okay, equalizers don't do well in terms of phases. They are typically designed to have linear phase, which we will study later. And what is this equalizer doing with respect to these frequencies, which is frequencies from 253 hertz to 1.3 kilohertz? What is it doing? It's damping them down. Okay, so effectively, if you were to plot this LTI system, effectively has, if you were to plot just the positive component of that, this LTI system has a response like this. Okay. Where this is about 1. These are positive frequencies, which is saying, well, keep these frequencies unchanged, damp these frequencies, and scale these frequencies a little higher. Okay. So an equalizer is the perfect example of an LTI system, and if nothing else, you should be able to design your own equalizers at the end of this class. But it's important for you to understand what do LTI systems do in terms of frequencies. They are doing exactly equalization modulo the phase aspect. Right? You put the knob too far down and you are going to kill the frequency. You put it high, you are going to amplify it a lot. You leave it there, you're not going to change the input frequencies. That's all LTI systems do in frequencies. Okay, so in general, LTI systems, as we talked about, the terminology, we'll look at some terminology of LTI systems. So each LTI system has an impulse response, and if we take its Fourier transform, it gives us h of j omega, which effectively tells us what is the LTI system going to do to the input frequencies, and because of that, this thing is called the Fourier transform of the impulse response. Because of this reason, is called frequency response, because it's telling us what will happen to the input frequencies. Now, general LTI systems, you can always design. It may be a hard task. A little bit of it is also art, which you will learn way later. You can design LTI systems with pretty arbitrary frequency responses. You know, someone could come and say, I want an LTI system because of their application whose impulse response is like this. Right? And it's supposed to be symmetric around 0. So someone could come and say, I want this h of j omega, and you could say, let me try to get a system which is very close to this. That's doable. But in general, while these are arbitrary LTI systems, there are some special types of LTI systems whose only purpose is to keep some frequencies as they are and kill other frequencies. Okay, and based upon that, they are given certain names. So we'll try to remind ourselves of those names. Okay, the other thing is LTI system and filter, the terms are used interchangeably. So LTI system or filter, we use the same, these two terms interchangeably. Sometimes we call it filter, LTI system, it's the same thing. Okay, so based upon certain characteristics of LTI systems or filters, they are given certain names. We'll study some of those names. The idea is leave most frequencies intact, kill other frequencies. So the first type is called a low-pass filter, or a low-pass LTI system. And as the name implies, what is the goal of this LTI system? Leave all frequencies as they are up to certain range omega c. Right? Or if you are talking about hertz, then fc. So you could say, I want all frequencies up to 1 kilohertz. And when I say positive frequencies, I'm implying the same to negative, okay? I want all those frequencies as they are and kill all frequencies above omega c. So the impulse response of that LTI system, if you look at it in terms of the frequencies, will look like this. It will be 1 up to omega c. So this is h of j omega. Okay. The amplitude is 1. Likely the phase is either 0 or it's a linear phase shift. Okay. And it's 0 everywhere else. So if you had a system with this frequency response, this is called a low-pass filter. And this filter is basically killing all frequencies above some frequency omega c. Okay. Sometimes we also actually get low-pass filters which look exactly the same, but the amplitude instead of 1 is, let's say, 5 or 10. They are still called low-pass filters. You just say that they don't have the gain of unity. Okay. So because they're keeping all the frequencies the same and killing other frequencies, and the frequencies that they are keeping, they are just amplifying them. The next class of filters is called bandpass filter. Again, I could give you the impulse response of this filter, but it's best to think of it in terms of the frequency domain. Right? If you want to, by the way, if you want to look at the low-pass filter impulse response, you just compute the inverse CTFT and you compute h of t. So we are not going to do that because you can always compute that. It's going to be a sink. So a bandpass filter is one which keeps frequencies in a certain region which away from 0. Okay, that's a bandpass filter. So a bandpass filter looks like this in the positive region, and of course the same in the negative region. Okay, so it basically kills everything. It has two values. One is omega c1, omega c2, minus omega c1, minus omega c2. The gain is typically called unity. So what is this filter doing? This is killing all frequencies around 0 and all frequencies above omega c2. So you could have a filter, you would say it bandpass filters between 1 kilohertz and 3 kilohertz. So it keeps all the frequencies between 1 and 3 kilohertz and kill everything else. Okay. And band pass filters are used pretty much every mobile phone that you have has some sort of a band pass filter in it. Because if you look at it, if you have heard these terms that FCC is auctioning radio spectrum, right? Every cell phone company is given a different portion of frequencies to operate on. Why? Because you don't want AT&T to interfere with Verizon, for example. So if you want to now, if you are using AT&T cell phone, it better be able to only focus on the frequencies that are given to AT&T. So how does it do that? It uses a band pass filter to kill all frequencies other than the ones that are given to AT&T. Okay. There is a flip version or inverse of the low pass filter, which is called the high pass filter. So a low pass filter kills all frequencies that are above a certain range. What does a high pass filter does? It keeps all the frequencies that are above a certain range and kill all the frequencies below that. So if you had to make a Fourier, if you had to draw the frequency response, it will look like this. Okay. It has still one parameter, omega c, but the difference between low pass and high pass is that a low pass filter, where if you say a low pass filter with 1 kilohertz cutoff, it means keep everything up to 1 kilohertz. If I say high pass filter with 1 kilohertz cutoff, it means keep everything above 1 kilohertz and kill everything below 1 kilohertz. Okay. And the last commonly used one is called a band stop filter, which is again the reverse of what a band pass filter is. So a band pass filter says keep frequencies in a certain region alive. A band stop filter says keep all the frequencies except in a certain band. Okay. So a band stop filter, its response looks like this. Again, just like the band pass, it has two parameters, omega c1 and omega c2, but the purpose of those two parameters is different because now it is saying between those two parameters you want to kill all the frequencies. Sometimes, for reasons that I can't explain right now, you design something which is called an all-pass filter. An all-pass filter, as the name implies, actually keeps all the frequencies. Okay, and an all-pass filter, the only thing it does is changes the phase. It manipulates the phase but keeps all the frequencies. So an all-pass filter will basically just be a unity gain. Okay. So these are the common types of filters. Just to give you an idea, let's say an example. I have an x of t signal, and if I look at its Fourier transform, then the Fourier transform looks like this. Its amplitude is 3, and it is 2 pi 1000, minus 2 pi 1000. So this is a signal which has only frequencies from 1 kilohertz to up to 1 kilohertz. And let's say I have a filter which is low pass filter with cutoff omega c. So I'll be using these abbreviations LPF for low pass filter. Cutoff of 2 pi 500 radians per second. So what this filter is doing is it's going to kill all frequencies in this input signal beyond 500 hertz. So if you were to look at y of j omega, what will that look like? that's going to be exactly the input signal Fourier transform up to 500 hertz. So the height of this will be 3. This will be 2 pi 500, 2 pi 500, because the rest of the stuff, everything beyond 500 was getting multiplied by 0, so that got killed off. Okay? So in this case, all frequencies above 500 hertz get killed. Okay. So that concludes our review of 345 in terms of signals and systems. And essentially from Monday's class, after the prereq quiz, what we will do is really start off this class, which is about discrete time. We'll first start off with understanding the same concepts of frequencies, but for discrete time signals and discrete time signals. And we'll define something called discrete time Fourier transform, which is very analogous to continuous time Fourier transform.